Hello and welcome back for some more reinforced concrete design. In this session, we are going to delve even deeper into the design of reinforced concrete columns. A column is a vertical structural element designed to resist axial forces and moments applied around principal axes of the column cross-section. Columns can have a rectangular, circular, or polygonal cross-sections and can be classified as short or slender. Structures can be classified as braced and unbraced. Braced structures are horizontally restrained. Horizontal forces are resisted in these structures by shear walls or other forms of bracing capable of transmitting all the horizontal loads to the foundations. Most concrete frames can be considered as braced because walls around stairs and lifts provide horizontal restraint. As a result, axial forces and moments are caused in braced structures by vertical loads. In unbraced structures, horizontal loads are resisted by the frame action of rigidly connected columns, beams, and slabs. Axial forces and moments are caused in this case by both vertical and horizontal loads. Both braced and unbraced structures can be further classified as sway or non-sway. The analysis of non-sway structures is based on the undeformed structural geometry, while structural deformation must be considered in the sway structures. Side sway is likely to significantly increase bending moments in columns. This increase of moment is known as second-order effect and is significant when it leads to more than 10% increase in design moments. Bending around all principal axes should be considered in the design of columns. For example, rectangular columns have two principal axes. Both must be considered in design. The design of a column depends whether it is short or slender. The decision on the type of column is made using the slenderness ratio, which depends on the effective height and geometry of the column cross-section. The expression for the slenderness ratio can be simplified for a rectangular column to 3.46 times the effective height over cross-sectional depth, while for the circular column to 4 times the effective height over cross-sectional diameter. Large lateral deflections of the column result in the development of secondary moments increasing the end moments from the framed action. This phenomenon is called the second-order effect. When the slenderness ratio is smaller than the limit value, the column is considered short and the second-order effect can be ignored. The slenderness limit is based on the creep ratio, reinforcement ratio, and the direction of moments at each column end. The second-order effects are generally avoided in the design, and more than 60% of all reinforced concrete columns are short. The effective height is the height of an equivalent column pinned at both ends. The effective height depends on the degree of fixity at each end of the column. The fixity depends on the relative stiffness of the columns and beams connected to either end of the considered column. The effective height affects the buckling capacity of columns. Here you can see different supporting conditions and the corresponding buckling deformation of columns. The supporting conditions from A to E are idealized. Real pin supports still resist rotation, for example due to friction, corrosion, and imperfections in support components, while the fixed supports cannot completely prevent rotation. Therefore, the supporting conditions F and G are really the most likely cases in structures in reality. The bracing conditions of the frame containing the column considered influences the column effective height. Here you can see the formulas used for the evaluation of the column effective height, depending on bracing conditions and the relative flexibilities of the rotational resistance at column ends. According to Eurocode 2, the relative flexibility of the rotational resistance at the column end is calculated depending on the column stiffness, the applied end moment, and corresponding rotation. According to the UK National Annex to Eurocode 2, the relative flexibility of the rotational resistance at a column end is calculated as a ratio between column stiffness and the sum of beam stiffnesses connected to the joint. The contribution of a column above or below the considered one to the rotational restraint of the joint is ignored. The stiffnesses of beams are halved to allow for the effect of cracking. For a symmetric frame with spans of similar lengths, the relative flexibility of the rotational resistance can be simplified to the product of the ratio between the second moments of area and the ratio between the column and beam lengths. After calculating the relative flexibility of the rotational resistance at both column ends, the effective height of a braced column can be found using the effective length factor given in the table shown in this slide. According to PD 6687, which is a background paper to Eurocode 2, the column effective height can be found using the method described in BS 8110. In this method, the effective height of a column in a plane considered may be obtained by factoring the original column length. The values of this factor are given in tables 3.19 and 3.20 of BS 8110 for both braced and unbraced columns as a function of end conditions. It should be noted that the effective height of a column in the two plane directions may be different. Here you can see tables 3.19 and 3.20. The end conditions in these tables are defined in terms of a scale from 1 to 3, where the increase in scale corresponds to a decrease in end fixity. Condition 1 describes a monolithic connection between column and beam or slab, where the beam or slab is deeper than the column dimension in the plane. This connection type is considered to carry moment. Condition 2 describes a monolithic connection between column and beam or slab, where the beam or slab is shallower than the column dimension in the plane considered. And condition 3 describes a connection between members not specifically designed to restrain rotation, but that can still provide some nominal restraint. Eurocode 2 defines the upper limit for slenderness ratio using the following formula. This method accounts for the effects of creep using the parameter A, the effect of reinforcement ratio using the parameter B, the effect of end moments using the parameter C, and the effect of ratio between the stress developed in the column cross-section and the design strength of concrete using the parameter N. When the effects of creep and reinforcement ratio are not known, the parameter A can be set to equal 0.7, while B can be taken as 1.1. Parameter C is calculated using the ratio Rm between the large and the smaller end moments, taking into account their directions. The value of Rm is taken as positive when the end moments act in opposite directions, giving rise to tension on the same side of the column. In this case, the parameter C is smaller than 1.7. The value of Rm is taken as negative when the end moments act in the same direction, giving rise to tension on different sides of the column. In this case, the parameter C is larger than 1.7. The parameter C can be taken as 0.7 for braced members in which the first order moments arise only from transverse loads or imperfections and is for unbraced members. When the effects of creep and reinforcement ratio are not known, the upper limit for the slenderness ratio for an unbraced member equals to 10.8 divided by a square root of the parameter N. The upper limit for slenderness ratios of an unbraced member is at its maximum when the end moments are equal and act in the same direction, making Rm equal to -1 and C equal to 2.7. In this case, the maximum value of the upper limit for the slenderness ratio equals 41.6 divided by a square root of the parameter N. The upper limit for slenderness ratios of an unbraced member is at its minimum when one end moment equals 0, making Rm equal 0 and C equal to 1.7. In this case, the minimum value of the upper limit for slenderness ratio equals 26.2 divided by a square root of the parameter N. When the slenderness ratio is smaller than its upper limit, the column can be treated as short. Otherwise, the column must be treated as slender, and we must take into account the second-order effects. Depending on the applied loads, columns can fail in different ways. The first failure type is compressive failure. It is an unlikely condition as most loads will produce some type of bending. Therefore, columns can fail in bending and compression. This type of failure is easily designed for when the structure is braced and the columns are not slender. Bending can occur in two planes, leading to biaxial bending failure. This type of failure is more difficult to account for. Slender columns can fail in buckling and therefore are designed to take account of second-order effects. Short columns usually fail by the crushing of concrete. Slender columns are liable to fail by buckling. In slender columns, side sway introduces an additional moment equal to the applied axial force times the column deflection. This moment causes further lateral deflections. Therefore, the additional moment becomes self-propagating until the column buckles. Generally, columns fail in different modes depending on their slenderness ratio, which can be large, intermediate, or low. Slender columns with high slenderness ratio buckle, while short columns with low slenderness fail by material crushing. Both of these modes of failure are important for columns with the intermediate slenderness ratio. The axial load causing column buckling can be found using Euler's formula, which is based on column bending stiffness. The axial load causing material failure can be found using the design material strength. In the case of a reinforced concrete column, the crushing axial load is found by adding the contributions of concrete and steel to the axial compression resistance of column cross-section. The ratio between the buckling force and crushing load determines the type of column failure. The diagram in this slide shows the relation between the buckling force to crushing load ratio and the slenderness ratio, where different regions represent different failure modes. If the buckling force to crushing load ratio is very high, column material failure occurs with negligible lateral deflection. This failure mode is typical for short columns, but can also occur in the columns with the intermediate slenderness ratio. When the buckling force to crushing load ratio and the slenderness ratio are in the intermediate range, the material failure is intensified by lateral deflection and additional moment. Columns in the region with low buckling force to crushing load ratio and high slenderness ratio fail by losing their stability, which is preceded by excessive deflections. This behaviour is typical for slender columns. Short columns can be in one of three structural states defined by strains in the concrete. State A is pure compression, with a compression strain smaller than 0.00175. State B is compression with some bending, where the compression strain at mid-depth is 0.00175. And strain C is compression with high bending, where the maximum compression strain is 0.0035, as in beams. The design bending moment of a slender column is found considering the influence of the first and second order effects. The moment is calculated as a maximum between three combinations of the maximum and minimum end moments: the moments produced by geometrical imperfections of the column and the moment produced by the second order effects. The moment produced by geometrical imperfections is calculated as the design axial load times the deflection due to imperfections, where the latter is found as the maximum value between the column effective height over 400, column depth over 30, or 20 millimeters. One of the moment combinations includes the sum of 60% of the maximum and 40% of the minimum end moments, plus the moment produced by imperfections. The moment produced by the second order effects equals the design axial load times the deflection due to the second order effects, where the latter is found depending on column curvature and effective length. Since the second order effects are ignored in the design of short columns, the design bending moment in such columns equals the sum of the maximum end moment and the moment produced by imperfections. Column reinforcement should be designed to carry axial load and bending moment. The reinforcement is required to carry the excess of axial load over the load carrying capacity of the concrete in the column cross-section. Additional reinforcement is required to carry the excess bending moment over the moment carrying capacity of the concrete in the column cross-section. Both reinforcement areas can only be found by solving iteratively the corresponding equations. To avoid this, design charts are derived for columns with rectangular or circular cross-sections, different symmetric reinforcement configurations, and different cover ratios. Here you can see a typical design chart. This chart defines the reinforcement requirements for different combinations of axial force and bending moment. Column reinforcement should be arranged symmetrically in the cross-section. In a rectangular column, minimum of 4 bars is required, where 1 bar is located at each corner. The minimum longitudinal bar diameter is 12 millimeters. The minimum area of longitudinal steel is evaluated based on the applied axial force and steel yielding strength, and it should be larger than 0.2% of the column cross-sectional area. To enable concrete to flow around steel bars, the maximum area of steel allowed outside laps is 4% of the column cross-sectional area, while at laps it is twice as much. The minimum diameter of links should be the largest of a fourth of the diameter of the compression bar and 6 millimeters. The maximum spacing of links is the least of 20 minimum diameters of compression bar, less a dimension of column and 400 millimeters. The maximum spacing should be reduced using a factor of 0.6 when it is larger than the larger lateral dimension of the column above and below a beam, or slab, or at lap joints of longitudinal bars with a diameter larger than 14 millimeters. Often, the column above a beam has a smaller cross-sectional dimension than the column below the beam. The continuity of longitudinal reinforcement can be achieved in these cases by cranking reinforcement in the lower column. Where the direction of longitudinal reinforcement changes more than by 1/12, spacing of links should be calculated considering lateral forces introduced by the cranked reinforcement. All longitudinal bars should be restrained by links to avoid buckling of bars in compression. Transverse reinforcement can be divided into two types. The first type is links or ties and is popular in the UK. The second type is helical or spiral reinforcement, which provides added strength and additional protection against seismic loading. The response of a reinforced concrete column depends on the type of transverse reinforcement used. Here you can see the force to axial deformation curves for a column with different transverse reinforcement, including links, light spiral, ACI spiral, and heavy spiral. As you can see, the spiral reinforcement makes the response of the column much more ductile, where the heavy spiral increases the column's strength. Continuity of longitudinal reinforcement in columns should be assured between floors. Cranked reinforcement in the lower column can be used when the upper column is smaller. In this case, the crank starts above the beam soffit so as not to reduce the moment resistance of the lower column. Links should be provided where the bars are cranked to resist buckling due to horizontal components of force in the inclined lengths of the bars. When the upper and lower columns are similar, longitudinal reinforcement can be cranked in the upper column. Links should be provided where the bars are cranked to resist buckling due to horizontal components of force in the inclined lengths of the bars. An alternative method for creating continuity in longitudinal reinforcement between floors is to use separate dowel bars, as shown here. I hope that was helpful, and I hope you join me again for some more reinforced concrete design.